Hello and welcome to section 1.8. We're going to talk about falling objects. So what happens if you have two objects with very different masses and you drop them from the exact same height? Which one hits the ground first? Well, hopefully you all answer the question in the correct way. They hit at the same time. Why is that? Because in the absence of air resistance, all objects dropped near a planet's surface fall with the same constant acceleration. That's called free fall. Now, if I were to drop a feather and a ball and try this, I might get a little different answer, and that's because we are not having negligible air resistance. That feather has a huge amount of air resistance in its shape, and so friction from the air definitely affects that. But if we have, say, two balls with really different masses, the air resistance is going to be very close to the same for both of those. This experiment actually was done on the moon by an astronaut who dropped a hammer and a feather on the moon's surface. And because of the lack of atmosphere on the moon, air resistance was negligible there. And so the hammer and the feather hit the surface of the moon at exactly the same time. So let's say we drop an object right here, or this little girl's dropping an object right there. And we set a camera up to take pictures at equal time intervals. We take a picture, and then at some time interval t, another picture. Equal time interval goes by, we get another picture. Equal time passes, another picture. We are seeing something here. If you'll notice, there is a greater displacement for every interval of time that passes. We have greater and greater and greater displacement happening. So you can clearly see that the velocity is not constant. That means that the object is accelerating. Now, every planet is different, but near the surface of the Earth, free fall acceleration is always this number, 9.81 meters per second squared. It would be 32 feet per second squared if we were using non-SI units. But acceleration due to gravity is what we call that acceleration. And it is represented by a lowercase g. That means acceleration due to gravity. It is negative. It's in the downward direction. So our acceleration due to gravity is negative 9.81 meters per second squared. The acceleration is in the downward direction, so we give it a negative sign. So what goes up must come down, right? If you toss a ball up, what happens? It travels back down. Here, if I toss that ball up, that ball gets to a point at the top where then it reverses direction and comes back down. Now, something very important to remember. A lot of people have trouble with this idea, but this ball is traveling at a certain velocity. The velocity is slowing down, but the acceleration is not. The acceleration due to gravity is the same throughout this entire motion. Here, my acceleration due to gravity is the same as it is here. It's reversing direction right here, but my acceleration is not changing. It is negative 9.81 meters per second squared at every moment in this motion, throughout the entire path of that ball. My acceleration is the same. The velocity certainly is changing. I'm starting out the pretty high velocity. It's slowing down. Velocity at some point is 0, and you see that on the graph. This is the very top of the trajectory of this object. At the top of its trajectory, its velocity is 0. You can see that the velocity starts out up here, and then down here, it is a very large negative velocity. That's where we're right down at this point on the motion of that object. Another point to point out is that from this point in time, we have the ball traveling to this point in time. The total displacement is also 0 because displacement considers direction, and the displacement here, as long as it was coming down in the same spot, if it went straight up and came straight back down, that displacement would also be 0. Now let's do some calculations. Here is an example of a problem or some questions we might ask ourselves and some calculations we could do. Up here, I wrote down all of the important formulas that we have looked at so far concerning acceleration. And these are all really important formulas, really useful formulas, and I put them all at the top so that as we work through this problem, you will hopefully be able to choose the correct formula. So let's read this example. Let's say a ball is thrown straight up into the air at an initial velocity of 25 meters per second. We're being asked to create a table showing the ball's position, velocity, and acceleration each second for the first 5 seconds of the motion of the ball. So let's write down the things that we know and the things that we need to know. Before I do that, I'm just writing down what they're asking me to do from the problem. I want to create a table. And in that table, I would like to know for each second, the time, I want to know the position, the velocity, and the acceleration of the ball. So that's what I did right here. For each second, at time equals whatever it's going to be. Let's start with 0.00 seconds. At 0.00 seconds, I'd like to know the position of my ball. Well, it hasn't gone anywhere, so the y-axis, it'll just be 0.0 meters, right? I'd like to know the velocity of my ball in meters per second, and I'm told that right here. Initially, it's 25.0 meters per second, and we know that acceleration due to gravity is always negative 9.81 meters per second squared. Now I'm asked to create this table and show for each second what all of these values are. So I know, now this is going to be a little squeezing it in. So I need to do this for at 1.00 seconds. Well, I know my acceleration due to gravity is the same, 9.81, so I'll just write that in. What I don't know my position, and I don't know my velocity. So those are the two unknowns. So let's write down, I need to know y, or I need to find y, and I need to find my final velocity. And those are the things that I'm going to need to calculate in order to complete this table. So let's try and calculate that final velocity. How would I go about doing that? I need to look at some of my useful equations up here, right? With what I do know and what I need to know, which of these equations are going to work best for me? If I look at, I want to find my final velocity. Does this equation work? Here's the final velocity. I know my initial velocity was 25 meters per second. I know my acceleration due to gravity. And do I know my time interval? I do. So actually, this is a really good equation to use because it will help me to calculate what I need to know. So when I plug those values in, I get my initial velocity, 25.0 meters per second, my acceleration due to gravity here, and my change in time from here to here is 1.00 seconds. I have one of these canceling out, so that gives me meters per second for units of that second term as well. And when I add those together, I get plus 15.2 meters per second. So I could write that in my table, plus 15.2. Now, this next thing I need to do, I'd like to find my position, so I could fill out this part of the table. So I need to look up at my very useful equations and see which one will help me to calculate my position. Actually, I could use two of these equations. This one here tells me change in position, and this one tells me change in position. And you can try it both ways, and they both give you the same answer. I'm going to use this one. I just think it's a little more simple. And if I plug my values into that equation, I will get I can write change in x or change in y, and I'm going to write change in y because when we look at an xy axis and think about that in terms of a graph, and we're dropping a ball, we're changing its up and down position. So I'm going to use change in y for my position and plug these values in. So when I fill those numbers in, my equation would look like this: 1/2 times the initial velocity, 25.0 meters per second, plus the final velocity. And my final velocity I just calculated right here, 15.2 meters per second. My change in time is just the change between these two, 1.00 seconds. And when I calculate that out, I end up getting a positive 20.1 meters for my change in position, and I can fill that in the graph. So now you go ahead and fill these out for all the way up to 5 seconds. So you can do your interval at 2.00, 3.004, and then 5 using these equations, and then flip to the next, or go ahead and restart the video, look at the next frame, and it has all the answers on it for you. Here is the answer page. It shows all of the answers to that previous problem. This was a very easy column to fill in because the acceleration due to gravity stays the same. And this was a pretty easy column. You're just going by 1 second increments. Hopefully you were able to get a correct value for these numbers. Okay, let's look at another example. Try practicing some of these ideas again. Let's say that a girl throws a ball straight up in the air, and it has an initial velocity of 6.0 meters per second. There's a little typo there on the slide, sorry about that. And let's say the ball starts at this elevation, it's 2.0 meters above the ground. How long will the ball be in the air before it hits the ground again? So let's start thinking about this problem. What is the first thing we should do? First thing we should do is take inventory. What do we know and what do we need to know? So there's a lot of information. We do know the initial velocity, right? 6.0 meters per second. That we do know. We also know acceleration due to gravity, right? Acceleration, sometimes it's written A with a little tiny g under it there. Acceleration due to gravity. We know that is negative 9.81 meters per second squared. That much we also know. We also know this. We know that the ball starts at 2 meters above the ground, and when this is all done, it will be on the ground. So our change in y, our displacement, will be a negative 2.0 meters because it will be 2 meters lower than where it started. So those are what we know. And what is it we need to know? We need to know how long. So our question is delta t is unknown. Now when I start looking at my equations, I'm also noticing there's something else I don't know. I don't know the final velocity just before that ball hits the ground. Obviously when it hits the ground, it will bounce and eventually stop. But right before it strikes that ground, the very moment, what is that final velocity? I don't know that either. So as I look at these equations, if I were to plug values in here, I could find time, but I don't know my final velocity. Here, I could find time if I used that equation. The difficult thing about using this equation, however, is that time is in time squared right here and time here. So this would be a really difficult math problem. I could do it and go ahead and try doing that if you'd like, but I'd like to avoid that because I have time in two different terms. I have it in just change in time and change in time squared. Well, here is an equation that doesn't use time at all, and I don't know time, so that's nice. This equation would allow me to calculate my final velocity because I do know all of these things. All of those different variables are known. So I could calculate my final velocity here, and then knowing final velocity, I could plug that into this equation to find my change in time. So let's do that. Let's use these two equations here. All right, I just rewrote my two equations because that's what I've done. In the first step, I look at what I know, what I don't know. My second step, I look at, and what I need to find, right, in the first step. My second step, I look at the equations I'm going to use and how I'm going to do that. And now I'm going to go on to calculating those equations. So all I'm going to do is substitute values into these two equations that I'm going to use. So I'm going to go ahead and do that. Okay, I've plugged the values in. I know that my initial velocity here was 6.0 meters per second, and acceleration here, my change in position was negative 2.0 meters. You can see that the units right here, these units are going to be meters squared over seconds squared, as these are also meters squared over seconds squared because I'm squaring all of that. So I'm going to go ahead and work that math out. So when 6 squared would be 36 meters squared per second squared, and when I multiply these out as well, I get another term. I add this term to this term. You should be able to get 75.24 meters squared per second squared. That is not the final answer, though. That is velocity, the final velocity squared. In order to actually find my final velocity, I need to, I don't know how to do this without making it get messy and confusing, but I need to take the square root of this side and the square root of this side. That will end up giving me my final velocity, and that will be either plus or minus 8.7 meters per second. And I know, you know that from math. 8.7 squared is going to give me 75.24. Or negative 8.7 squared will also give me 75.24. And in this case, we're going to have to choose which one is the correct value. And the correct value is going to be negative 8.7. And so I'm going to scribble out the positive sign because that one won't work. And the reason it's negative is because the ball is moving down. And my final velocity as the ball is moving down is, right before it hits the ground, negative 8.7 meters per second. I didn't leave myself very much room here, but if I take a look at the second equation, because I'm not done, all I did was find the final velocity. And what do I really need to find out is how long it's going to be in the air. This is really what I'm wanting to know, right? And I need to use this equation to find that, the time that it's in the air. And I now know all these other things. I know my final velocity, I just found it. I know my initial velocity, it's right here, 6.0 meters per second. I know my acceleration due to gravity is always negative 9.81 meters per second squared. So when I plug those values into this equation right there, I should come up with delta t equals 1.5 seconds. And that's actually my answer. That's what I want to know. Limited by 2 sig figs here. That's the correct sig figs. Go ahead and plug those values in. Punch them out on your calculator. Make sure you're getting the same answer that I'm getting, and that you're doing that correctly. And then you can practice some more of these problems on your practice problem sets. If you're interested in some advanced work, this is a really good time to read a little bit about time dilation. What is that? Wow. Read pages 66 and 67 in your textbook. It explains what that concept is. And it has to do with special relativity, really interesting. And another consequence of the theory of relativity, special relativity, is length contraction. Length contraction is another phenomenon, and its formula is right there, that equation. And I don't remember, but just a quick review. Anytime you see a not, a zero like that, it means initial. So the L here, in this case, would be length, and L naught would be initial length. So your job then for your advanced idea here is to try some different values for speed in the different equations for velocity. How fast does something really need to go before time dilation and length contraction become significant? So look into that, and I look forward to seeing you in class.